Okay, so let's continue for our chapter of electrostatics. So let's proceed to a new subtopics, which is the motion of a charged particle in a uniform electric field. Motion of a charged particles in a uniform electric field. Okay, so this is actually represented in an experiment. So consider I have two plates. So this one is the first plate and this one shall be the second plate. Okay. So this is the second plate. Okay, consider this one of the this plate is actually positive. So I denote positive as the green color. So this is the positive. This is positive, 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 and finally positive. Okay, so as for the negative plates, we have negative, 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 negative. Okay, and finally negative. Okay, so um, the electric field is actually moved from the positive plates to negative plates. Okay, I should use this one as the black color. Alright, so this one is the second electric field. And this one is the third one, fourth, 5, 6, and finally 7. Okay, so the direction of the electric field is basically is from the positive to negative. So this is the region of the electric field form. Okay, so consider I put the normal metal plates at the end of this two metal plates, two charged metal plates, which which will help us to produce the electric field. So this is the normal metal plates. Okay, consider we have the charged particle that we use is actually E. So this E initially is actually moving in the horizontal velocity. So horizontal velocity, we denote this one as U. So this U is represented as the initial velocity in the form of horizontal velocity. Okay, so let me see whether I missed something. Okay, so this one shall be my L. Alright. And this one, I denote this one as L. And as for another distance, which is the distance at the end of the electric field, and this metal plates, so this one shall be my capital letter D. Okay, so we know that when this electron entering the region of the electric field, so this electron will eventually deflected. So since the electron is negatively charged, so what we know is the electron will eventually deflected towards the positive plates. So what we have for the path of the electrons eventually is some sort of this path. So this one is a parabolic curve. And okay, so initially the electrons entering this region of the electric field, so this point, we consider this point as point A. So after passing through the electric field as the electron being deflected. So the point where the electron is about to exit the region of the electric field is actually B. So this point is the point where the electrons actually stops. So this point is we consider this point is actually C. Okay, so from here, so we have this distance, the vertical distance. So I consider this vertical distance is y. So this y is actually represent how what is the distance of the deflection of the electrons uh, after leaving the region of the electric field. So this one shall be my theta. Okay, and this one is the theta. Alright, so there's another distance which is this one. So this one I shall denote this one as my h. So this h actually telling us what is the vertical distance. What is the vertical distance that the electron actually deflects while in the region of the electric field. So I repeat again. So this h is actually the distance for the deflection of the electrons inside the region of the electric field. So um, how should I describe this? What is the distance after the electron being deflected? Okay, yeah. What is the distance after the electron being deflected by the electric field? Alright, so yeah, that's it for the all the information that we have. Okay, so let me see for a while. Okay, let me observe for a while. Okay, so alright, so this one. Okay, so our main objective um is actually used to find out the velocity after the electron being deflected by this region of the electric field. So our velocity basically is in here at point B. So our main objective is aim to find the velocity at point B. So this is the main objective. So as you can see that what I wrote here is actually there's a theta here. So this theta is actually means the degree of electrons from B to C. So this degree actually telling us that the final velocity for the electron is actually a resultant velocity which consists of vertical components and horizontal components. Okay, so what we need to find is actually the final velocity. Okay, so first of all, as we observing this the path of these electrons, we know that the electron is actually being deflected towards the positive plates. So since the electron being deflected towards the positive plates, so this is actually creating upward force. So this is the upward force towards the positive plates. So this vertical force, which is pointing upwards, is actually the electrostatic force exerted by electrons. So my F basically is equals to the electric field times the charge. So since the charged particle that we use is electron, so what we need to do is actually put this one as E, and this is F. Okay, so in this case, F is actually equals to MA, so which is equals to EE. So what I have for my acceleration is actually EE over M. So this acceleration is actually pointing upwards, since the electrostatic force is pointing upwards. So this is the first information. A is equals to EE over M. Okay, so let me just erase this one. Alright. Okay, so this is the first information that we have. Okay, as for the second information, so what we need to find is actually find out the time taken for the electrons to move from A to B. Okay, so okay, let me just observe for a while. So we know that the velocity is actually s over t, which is the rate of change in displacement. Okay, so in this case, initially we know that the electron is actually moving in the initial velocity, which is u. So this u, which is in the form of horizontal motion, so while entering this region of the electric field, so the E so this initial velocity will actually be deflected. So the time taken to move from A to B is actually U is equals to L over T. So what I have here to so this is actually describing the initial velocity. So the time taken for the electrons to move from A to B is actually L over U. So this is the second information. T is equals to L over U. Okay. So to be note that what we're describing for the first information, which is acceleration, and the second information, which is time taken. So these two information is actually describing the electron inside the electric field instead of this outside the region of outside of the electric field. So this is I repeat again. So this is the acceleration is actually describing the electron inside the region of the electric field. So same goes to this time taken for the electrons to move from A to B. Okay, so this is the second information. So as for the third information, so we have A, we have T. So what we need to find out is actually this H. So what will be our H then? Okay, so let me observe for a while. Alright, so this H, so since this H is actually the vertical distance, so what we have for the formula is actually S equals to UT plus half AT square. So this since the initial vertical velocity, which is the before the electrons entering the region of the electric field, so since the vertical velocity is sorry, let me say again. So since the motion of the electrons initially is in the form of horizontal motion, so I can conclude that my vertical velocity is actually 0. So this is 0 and this is 1 over 2 at square. So this is my h. So this one as well, we're describing um, the electrons which is moving inside this region of the electric field. So this is half, and what will be our acceleration here? So my vertical acceleration is actually E over m. So the time taken for the electron to move from A to B is actually L over U, and this is square. Okay, so this is the third information, which is the h. So let me just erase this one. Alright. So this is the third one. So the third one we have here is actually h is equals to the half E over m L over U square. Okay. So for the third information. So let's move on to the vertical velocity after being deflected by the region of the electric field, after exiting the region of the electric field or leaving the region of the electric field, which is the same. So my vertical velocity, which is Vy, is equals to U plus At. So initially, so I explain again. So initially, the initial velocity is actually U. So enter this region of the electric field is actually U as well. So after leaving the region of the electric field, so the resultant velocity is actually I should write this one as V. So this shall be our final velocity. So okay. So this one shall be our final velocity, and this one is the initial velocity until E is actually the electron is actually moved from A to B. Okay, so since my initial velocity is horizontal motion, so my U is actually 0. So A is EE over M, so my T is actually L over U. So this is my Vy, and this is EEL over MU. So this is the vertical velocity after leaving the region of the electric field. Okay, so alright, so that's it for the vertical velocity. So what about the horizontal motion? So as for the horizontal motion, so what we have is actually S is equal to Vt. Okay, so R is equals to, let me just observe for a while. So this is the horizontal motion. So my L, okay. So let me just observe for a while. Okay. So what will be my L here? Alright. So my displacement is actually the L. So this is my Vx. So the time taken for electron to move from A to B is actually L over U. So L can be cancelled, and hence what I get for the horizontal velocity is actually U. Yeah, this is the horizontal velocity. Alright, so let me just observe for a while whether it's correct. Okay. So this one is the acceleration, and this one is the time taken for the yeah, I think this is the answer for vertical velocity and final and the horizontal velocity. So I repeat again. So since v is actually equals to u plus at, so this vertical velocity, and since my initial velocity is a horizontal motion, hence my u is actually 0. So my my acceleration is actually e over m. So this t is actually L over U. So what I get is actually EEL divided by mu. So this is the vertical velocity. So as for the horizontal velocity, so the horizontal velocity is actually the this is the final velocity, which is at here. Okay, so let me just draw it more properly. So this one is Vx and this one is Vy. So this is the V. Excuse me. So this one, so what I get is actually Vx is equals to U. Okay. So the um so if we wish to find the resultant velocity, so the concept is actually basically the same. So V is actually equals to the Vx square plus Vy square. So this is the magnitude. As for the direction, the tangent is actually equals to the Vy over Vx. So in this case, what we have here is actually the V. So this is the V, and okay, and since this is the resultant velocity, so this region, okay, from B to C, so this region is actually the resultant velocity. So we can see that the tangent is actually equals to the hypotenuse divided by the adjacent. So what we have here for the tangent is actually equals to y over d. So this is the direction of the final resultant velocity. Okay, so we have done for this um, motion of a charged particle in a uniform electric field. Okay, so let me just erase all this one. So let's move on to the new subtopics. So let's just move on to Gauss law. So before that, um, before entering the Gauss law, there are some principles that we need to understand. So let me draw a metal plate here. Okay, so consider this is the metal plates. So, okay. So consider the electric field passes through these metal plates. So, okay. Okay, alright. So consider the electric field um, passing through these metal plates from the back to the front. Okay, so we know that the electric field, which is represented as the electric field lines. So okay, so let me see for a while. So consider the electric field lines. Electric field lines passing through per unit area. So so what we need to know is actually the electric field lines passing through per unit area. So this is actually represented as electric field strength. Electric field strength, which is the force per unit area as we discussed from the previous parts. So this is the electric field strength. So electric field strength in this case is actually the electric field lines passing through the metal plates per unit area. As for the okay, so from here we have another new how should I say another new thing, which is the total number of electric field lines. Total number of electric field lines. Total number of electric field lines passing perpendicular through the surface area. Passing. So this is actually the perpendicular to the surface area of the metal plates. Perpendicular through the surface area. Surface area. So this is the electric field lines passing through the metal plates per unit area, or 1 meter square of the area of the metal plates. So this for another one, which is the new thing, so which is the total number of electric field lines passing through the surface area of the metal plates. So the surface area is actually meant by the total surface area that passes through by the electric field lines. So this, what we call, is actually the electric flux. So electric flux is actually has a symbol which is phi. So this is the symbol. Alright, so electric field strength is actually the total number of electric field lines passing through per unit area of the metal plates. The electric flux is the total number of electric field lines passing through perpendicularly through the surface area of the metal plates. So the electric flux, for the formula, the electric flux, what we have here is actually the cross products of the electric field lines to the surface area of the metal plates. So for example, this is the metal plates. So this is the cross product. It means that the electric field lines is perpendicular to the surface area. Okay, so or we can write it in the another form, which is EA sine theta. So if the sine theta is actually 90 degree, so sine 90 degree is actually 1. So I can conclude that my electric flux which pass through the metal plates is actually maximum. Okay, so if the degree is actually 0, so the electric flux will eventually become 0. So this is the formula for electric flux. Okay, so this is the new principle. Okay, so we're going to explain what is actually meant by Gauss' law. So Gauss' law actually states that the net electric flux okay, which is phi passing through okay, a closed surface. So a closed surface is actually meant by the metal plates, for example, as we closed surface as we represented just now. Okay, so a closed surface is actually can be stated as the Gaussian surface. Okay, so Gaussian surface is equal to the total net charge okay, let me see, inside the closed surface divided by the permittivity of medium. The permittivity of medium. So what we have for the formula of Gauss' law is actually the electric flux passing through the Gaussian surface is actually equals to the total net charge divided by permittivity of medium. So this is different medium has the different permittivity of how should I say has different permittivity. Okay, so if the experiment is actually conducted in the vacuum, so what we have here is actually the permittivity of vacuum, which is epsilon naught. Sorry. So which is epsilon naught. Okay, so we have done for this definition. Alright, so let's just move on to another part. So this is actually also still in the topics of Gauss' law. So what we need to see is actually the application of Gauss' law. Application of Gauss' law for a point charge. So basically, a point charge, let's say this is a positively charged. So the positively charged the electric field lines produced by the positive charge is actually pointing upwards. Sorry. So this is the electric field line. So the electric field line is actually pointing outwards from the positively charged. So pointing outwards, pointing outwards, pointing outwards, pointing outwards, and finally pointing upwards. So the electric field lines produced by how should I say, produced by these positively charged particles. So when this positively charged particle producing the electric field lines to the surroundings, so there is actually a Gaussian surface for the point charge, which is perpendicular to the electric field lines. So this is perpendicular, and same goes to the others. So we can see that this Gaussian surface, is actually perpendicular to the electric field lines produced by the positively charged. Okay, so based on the Gauss law, the electric flux passing through the Gaussian surface is actually equals to the net charge divided by permittivity of medium. So in this case, inside this Gaussian surface, so this case is actually, we consider this one as vacuum. So vacuum has the value of epsilon naught. Okay, so this is the first one. So as for the second one, second formula, so the electric flux, what we know is actually equals to EA. So since the surface and the electric field lines are perpendicular to each other, so what we have for the electric flux is actually EA. So equaling both equation, Q net divided by epsilon naught, and this is EA. Alright, so in this case, the surface area for a point charge, which is in the three dimension. So the three dimension for the point charge is actually a sphere. So this is the 4 pi r square. So this is the Q net divided by epsilon naught. So what we have here for the electric field strength for a point charge is actually Q. So it's not necessary for us to keep writing for the Q net. So since there is only one charge, which is the positively charged for a point charge, so 4 pi epsilon naught r square. So this is the formula of the electric field strength. So what we can do is actually simplifying this formula by converting this 4 pi epsilon into one constant, which is kq over r square. So this k, the value of this k is actually equals to 9.0 times 10 to the power of 9. Alright, so this is the application of Gauss law for a point charge. So what happened to the application of Gauss law in a spherical conductor? So this is the spherical conductor. So consider I have a spherical conductor. So inside this spherical conductor there are the different charges, which is positive Q1, negative Q2. So same principle, this spherical conductor, which will produce electric field lines. So consider the electric field lines is actually pointing upwards. Consider the net charge is actually still positive value. So the electric field lines is actually pointing upwards. And this one outwards as well. So between this region of the electric field, there is actually a Gaussian surface. So same principle for the point charge. So inside this Gaussian surface, the space is actually in the form of vacuum. So this is Gaussian surface. So as for our electric flux, which is equals to the total net charge divided by permittivity of vacuum. So what we have here for the net charge is actually Q1 plus a negative Q2. So this is the net charge. Okay, so this is the first one. So this is only the example that given by me. So this is actually not the actual net charge. So this is only the example. Okay, so as for the another electric flux, which is EA, so we need not to worry that what is the angle between the electric field line and the Gaussian surface, since both of them are actually perpendicular to each other. Okay, so equating 1 and 2, so Q1 negative Q2 divided by epsilon naught equals to EA. So in this case, the spherical conductor is also 4 pi r square as well. So this is Q1 negative Q2, which is the net charge. So finally, the electric field strength, what we have is actually Q1 minus Q2 divided by 4 pi epsilon r naught. So this is 4 pi epsilon naught can be simplified k Q1 minus Q2 divided by r square. So this is the spherical conductor for the application of Gauss law. Alright, so what we need to know for this addition notes. So let me just erase this one. Okay. So as for the addition, what we need to know inside this sphere, inside the sphere, so inside the sphere, the electric field strength is actually equals to 0. Electric field strength is actually equals to 0. So why is this so? This is because, okay, the spherical conductor, so let me just write it down. So once I have done writing, I'll explain later. So the spherical conductor is actually a equipotential body. So this is actually our keywords. So equipotential body. So a spherical conductor is actually is an equipotential body. So since the equipotential, so let's say okay, for this point charge, which is Q1, inside this spherical conductor, I have the 13 volts. As for the Q2, which is negative Q2, is actually 13 volt as well. Since the every point in this spherical conductor is actually 13 volts. Sorry, it should be 30 volts. So every point in this spherical conductor is actually 30 volts. So since the 30 volts, since all the region of this spherical conductor consists of 30 volts. So hence I can conclude that there is actually no potential difference. There is no potential difference. So without potential difference, and hence the electric field is actually equals to 0. So what is actually the relation between the uh, electric potential and electric field strength? So in this case, the electric field strength is actually equals to negative dV over dr. So why there is a negative in front of this dV over dr? So let me just, okay. So consider I have my V. So this is V and this is KQ over R. So what I have to do to get the electric field strength is um, actually differentiate this electric potential. So what I have here is actually dV over dr. So what I get is actually negative kq over r squared. So we know that whatever the electrostatic force, the equipotential how should I say, equipotential energy, the potential electric potential energy, sorry, electric potential energy and electric potential, both all of them are actually can be repulsive and attractive, since the force can be repulsive and attractive. So this negative show us that the electric potential is actually consists only attractive. So what we need to do to show that this electric potential can be positive or negative, so what we need to do is actually adding a negative. So this adding a negative, so what we have here is actually kq over r squared. So this kq over r squared means the so this kq over r squared is equals to the electric field strength. So let me just substitute this one inside here. Alright, so after differentiating the electric potential, so kq over r squared, so what I have is actually the kq over r squared without the negative. Okay, so I think that is the I haven't finished yet. So in this formula, which is E is equals to the dV over dr. So since the every point in this spherical conductor, inside this spherical conductor is actually is 30 volts, so hence there is no potential difference. Hence there is no change in the electric potential, and the potential gradient for the spherical conductor is considered to be 0. So the potential gradient is equals to 0. Hence, the electric field strength inside this spherical conductor is 0. That is why we said that the electric field strength inside the spherical conductor is 0. Alright, so okay, so let just So let me just erase this one. Okay, let me just erase this one as well. Alright, so what will be the graph for the electric field strength? Oops, sorry. So the electric field strength, the graph of electric field strength against the distance. So in this case, this is actually inside the spherical conductor, and this is R and this is negative R. So what I have here, the electric field strength inside this spherical conductor shall be 0. So as for the outside of the spherical conductor, outside on the surface of from the surface of the spherical conductor until infinity, so the electric field strength varies with the distance is actually in the form of this curve, which is reciprocal graph. So my electric field strength is equals to the Q divided by 4 pi epsilon naught r square. Alright, so as for the negative parts, the graph is as well same go with the reciprocal graph. So this is the graph of electric field strength against the distance. Alright, so I think we have done for this parts. Okay. So let me just find out. Right. Okay. So just now we talked about the spherical conductor. So what if the conductor is actually not in spherical? So let's say this is a cubic. Okay, let me use the black color. So let's say this is a cubic conductor. So what I have here is the cubic conductor. So the electric field is actually passing through from the left to the right. Okay, so this is the cubic conductor. So what we know is actually the EA. The electric flux passing through this cubic conductor is actually EA. As for another, so since the electric field is perpendicular to the surface, so the electric flux is actually maximum. So this, as for another one, the Q net, which is the net charge divided by the permittivity of this cubic conductor. So equating both equation, so this is Q net and this is epsilon, and this is equals to, okay, let me just think for a while. Okay, so this is the EA. So since this conductor is no more a spherical conductor, so what I need to do is actually just leave it this A as the remain this surface area as A. So what I have here for the electric field strength of this cubic conductor, which is Q net divided by A over epsilon. So what I have here, the QA is actually another new formula, which is sigma. So this sigma is actually represent the surface charge density of the charge plate. Surface charge density of the charge plate. So this sigma is actually represent the surface charge density of the charge plate. So this is the surface charge density. Sorry, this is the surface that contact with the electric field strength. So I can conclude that my Q over A is actually equals to the surface charge density of the cubic conductor divided by the permittivity of the um, medium. Okay, so this is the another formula for electric field strength. Alright, so we have done for electric field strength. Okay, so I think we stop here and we will continue the another subtopic on the next video. So I'll see you next time. Thank you. Bye.